I want you to think about the last time you turned on a light switch. You flicked it, the light came on instantly. Simple, right? Now, here is the question your school physics teacher almost certainly never asked you. How? Not what is electricity? Not what is voltage? But how, precisely, does the energy get from that switch on the wall to the globe in the ceiling? Because here is the thing. The answer your textbook gave you, the one about electrons flowing through the wire like water through a pipe, is wrong, not slightly wrong, not approximately wrong, fundamentally, completely wrong. And I do not mean that to be dramatic. I mean it in the precise, rigorous physics sense that Richard Feynman spent years trying to correct. Because Feynman, when he taught electricity at Caltech, refused to let his students leave with the comfortable simplified version. He insisted they understand what was actually happening. And what is actually happening is so much stranger and so much more beautiful than anything in your Year 11 textbook. Today, we fix that. By the end of this video, you will understand electricity at a level that most university physics graduates do not reach until their third year. Let us go. G'day and welcome back to Curious Physics AU, the channel where we take physics seriously enough to tell you the truth, even when the truth is more complicated than what fits in a textbook. I am Abdullah, and today we are tackling one of the most misunderstood topics in all of high school physics: electricity. Now, before anyone panics, this is not a maths-heavy video. We are not going to drown in equations. We are going to think carefully, clearly, the way Feynman always insisted we should, because Feynman had this principle. He called it the difference between knowing the name of something and knowing something. You can know all the right words, voltage, current, resistance, circuit, and still have absolutely no idea what is actually happening physically. Today, we are going for actual understanding. And I promise you, by the end of this video, electricity will never look the same to you again. Let us start with the lie. Here is what your school textbook almost certainly told you about electricity. Electrons flow through a wire from the negative terminal of a battery to the positive terminal, like water flowing through a pipe. The electrons carry energy from the battery to the globe. The globe converts that energy to light and heat. Simple. Now, let us take that apart, piece by piece. First, conventional current versus electron flow. Here is an embarrassing piece of physics history. When scientists first started studying electricity in the 1700s, they had to choose a direction for conventional current to flow. They chose from positive to negative. Benjamin Franklin made this convention popular. There was just one problem when we later discovered that electrons are the actual charge carriers in metal wires. We found they flow from negative to positive, the opposite direction to conventional current. So right from the start, every circuit diagram your teacher ever drew shows current flowing in the opposite direction to the actual electrons. Your teacher knew this. They just did not want to confuse you. Fair enough for Year 9. But we are going deeper today. Second, and this is the bigger problem, the water pipe analogy is dangerously misleading. In a water pipe, water molecules carry energy from one place to another. They start at the pump, full of energy. They travel through the pipe. They arrive at the destination, having delivered their energy. If electricity worked like water, turning on a light switch in your lounge room in Sydney would take a measurable amount of time, because the electrons would have to physically travel from the power station all the way to your house first. At the actual drift speed of electrons in a copper wire, which is roughly 1 millimeter per second, electrons from the power station would take years to reach your light globe. Years, but your light turns on instantly, in a fraction of a millisecond. So electrons are clearly not carrying energy from the power station to your globe, like water carrying energy through a pipe. Something else is happening entirely, something far more interesting. Let us talk about electron drift speed properly, because this blows most people's minds. In a copper wire carrying a typical household current, the electrons are drifting at roughly 0.1 millimeters per second, sometimes less. For context, a garden snail moves at about 50 millimeters per second. Your electrons are moving 500 times slower than a garden snail. Now, here is the thing that confused students for generations. If electrons move that slowly, how does your television turn on the instant you press the remote? How does your phone charge? How does the traffic light change? The answer is a concept called the electric field. When you connect a battery to a circuit, you are not sending electrons from the battery to the globe. You are establishing an electric field throughout the entire circuit, almost instantaneously, at close to the speed of light. Think of it this way. Imagine a pipe completely full of marbles, packed end to end with no gaps. When you push one marble in at one end, like a marble pops out at the other end instantly. Not because the same marble traveled the whole length, but because the pressure pulse propagated through the entire line simultaneously. Electrons in a wire behave similarly. The wire is already full of electrons. When the electric field is established, all the electrons in the circuit start moving simultaneously. The signal propagates at close to the speed of light. The individual electrons barely move, but the electrical signal, the disturbance in the electric field, travels almost instantaneously. So the answer to why does the light turn on instantly is not about electron speed at all. It is about electromagnetic field propagation. And that brings us to the truly mind-bending part of today's video, the part that Feynman was most insistent about. Where does the energy actually flow? This is the section that rewires everything, and I genuinely mean rewires, because what I am about to tell you completely changes the physical picture of how a circuit works. In 1884, British physicist John Henry Poynting published one of the most important and least appreciated results in all of electromagnetism. He proved mathematically, using Maxwell's equations, that the energy in an electric circuit does not flow through the wire. The energy flows through the space around the wire, through the electromagnetic field in the empty space surrounding the conductor. This result is called the Poynting vector. It describes the direction and magnitude of energy flow in an electromagnetic field, and it points not along the wire, but perpendicular to it, from the space outside the wire into the wire. Let me make this concrete with an Australian example. Right now, somewhere in New South Wales, a power station is generating electricity. That electricity travels along high voltage transmission lines to homes and businesses across the state. Your school textbook picture of this process, electrons carrying energy through copper wires like water through a pipe, is wrong. The real picture is this: the transmission lines create electric and magnetic fields in the space around them. The energy flows through those fields, through the air and space surrounding the wires, guided by the conductors, and flows into your home and your appliances. The wire is not a pipe carrying energy. The wire is more like a guide rail, shaping and directing the electromagnetic fields that carry the energy through the surrounding space. Here is a thought experiment Feynman loved. Imagine a simple circuit, a battery connected to a light globe with two wires. The moment you complete the circuit, where does the energy come from to light the globe? The intuitive answer: from the battery, through the wire, to the globe. The correct answer: the energy flows from the electromagnetic field in the space between the battery and the globe. The field that exists outside the wire. The field you cannot see. The wire guides it. But the energy travels through the field. This is not a subtle correction. This is a completely different physical picture of what electricity is. All right, now that we have shattered the water pipe model, let us rebuild our understanding properly. Voltage. Your textbook probably defined it as electrical potential difference, the push that drives current around a circuit. That is not wrong, but it is incomplete in a very important way. Voltage is more precisely defined as the difference in electric potential energy per unit charge between 2 points. But here is what most school courses never tell you. Voltage is a property of the electric field. It exists in the space between conductors, not inside the wire itself. Here's a simple way to think about it. Imagine two hills of different heights. The difference in height between them, that is analogous to voltage. The tendency of a ball to roll from the higher hill to the lower hill, that is the electric force driving charge around a circuit. But here is the key. The height difference exists in the space between the hills, not in the hills themselves. The landscape around them determines the dynamics. Similarly, voltage exists in the electromagnetic field surrounding the conductors, not inside the copper atoms of the wire. This is why you can measure voltage across an open circuit, even with no current flowing. The electric field, and the potential difference it creates, exists in the space between the terminals even when no charges are moving. When Feynman taught this to his Caltech students, He drew the electric field lines around a simple battery and wire circuit, not through the wire, around it, in the space outside. And then he asked, so where is the energy? In the field, in the space, around the wire? That is voltage. That is the real picture. Now, let us talk about resistance, because the school explanation of resistance is also missing something crucial. Ohm's law. Voltage equals current times resistance. V equals IR. Every Australian Year 11 student knows this equation. But what is resistance physically? Your textbook probably said something like, resistance is the opposition to current flow, caused by electrons colliding with atoms in the wire. That is true as far as it goes, but it misses the deeper picture entirely. Here is the Feynman level explanation. When an electric field is established along a wire, it accelerates free electrons. Those electrons gain kinetic energy. Then, almost immediately, they collide with the vibrating lattice of metal atoms in the wire. In that collision, the kinetic energy of the electron is transferred to the atom. The atom vibrates more energetically. The wire heats up. Then the electron is accelerated again by the field. Collides again, heats the wire again. This continuous cycle, acceleration, then collision, is what we experience as electrical resistance. And the energy being transferred in those collisions and the energy heating the wire came from the electromagnetic field outside the wire, flowing in through the Poynting vector. Here is a cracking analogy. Imagine the Sydney to Melbourne Hume Highway completely packed with cars travelling at the same average speed. Now imagine there are random roadblocks every few kilometres that slow each car briefly before it accelerates again. The average speed of traffic stays roughly constant. But at each roadblock, energy is being dissipated. Heat, noise, friction. That is resistance in a wire. The electrons are the cars, the metal lattice atoms are the roadblocks, and the energy being dissipated at each collision. That is Joule heating. That is why wires get warm when current flows through them. And here is the beautiful physics connection, and the energy for all of that heating came from the electromagnetic field, not from the electrons themselves. The electrons are just the mechanism. The field is the energy source. Ohm's law describes the relationship correctly, but it does not tell you where the energy actually comes from or where it actually flows. For that, you need Poynting. Right, let us go back to where we started. That light switch in your lounge room. You flick the switch, the light turns on instantly. Now, with everything we have covered today, let us describe what is actually happening. The real physics. The moment you complete the circuit by flicking the switch, an electromagnetic field propagates outward from the switch throughout the circuit at close to the speed of light. Not through the wire, around it, through the space surrounding the conductors. That propagating electromagnetic field is described by the Poynting vector. It carries energy from the power source through the space surrounding the transmission lines and house wiring to the light globe. The electrons in the wire begin to drift very slowly, nudged by the electric field component of the electromagnetic wave. At each point along the wire, the field drives electrons through the resistive metal lattice, transferring field energy to thermal energy. In the filament of the globe, or in the semiconductor of an LED, that energy transfer is concentrated and dramatic. The temperature rises. Light is emitted. The globe glows. The whole process, from switch to light, takes roughly the time for an electromagnetic signal to travel the length of the circuit. At near the speed of light, that is microseconds. Not because electrons rushed from the power station, but because an electromagnetic field propagated through space at the speed of light. That is the real physics of your light switch, not electrons flowing like water. Electromagnetic fields propagating through space, guided by conductors, carrying energy in the field itself. Feynman would be satisfied with that answer. Your Year 11 textbook, not so much. Now, I want to be fair here, because some of you might be thinking, why did my teacher lie to me? They did not lie. They simplified. And there is a genuinely important reason for that. The water pipe model of electricity, electrons flowing like water through a pipe, is a brilliant teaching tool for building initial intuition. It gets students to the right answers for circuit calculations. It predicts current, voltage, and resistance correctly at the level of Ohm's law. For building toasters, charging phones, and wiring houses, the simplified model works perfectly well. The problem only appears when you ask deeper questions. Why does the light turn on instantly? Where exactly is the energy? What is voltage really? The simplified model breaks down, and if you have only ever been given the simplified model, you have no framework for the deeper questions. This is what Feynman objected to. Not the simplification itself, but the failure to flag it as a simplification. The failure to say, this is a useful model, but it is not the whole truth. Science education at its best teaches you both, the useful simplification and its limits, so that when you encounter deeper questions, you are not confused, you are ready. That is exactly what we just did today. You now have both the map and the territory. And here is the beautiful consequence of everything we have covered today. The payoff that makes the whole journey worthwhile. If electricity is really about electromagnetic fields propagating through space, then electricity and light are the same phenomenon. James Clerk Maxwell, the Scottish physicist who unified electricity and magnetism in the 1860s, showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields, and that these two fields can sustain each other, propagating through empty space as a wave. He calculated the speed of that wave. It came out at 300,000 kilometers per second. The speed of light, Maxwell realized, and it must have been one of the most astonishing moments in the history of science, that light is an electromagnetic wave, the same phenomenon as the fields propagating through your house wiring, just at an enormously higher frequency. The electricity flowing through the wire in your bedside lamp and the light that lamp produces are both electromagnetic phenomena, different frequencies of the same underlying physical reality: radio waves, microwaves, infrared heat, visible light, ultraviolet, X-rays, gamma rays, all electromagnetic waves, all the same phenomenon, all described by Maxwell's equations, all related to the electricity in your circuits, the light switch in your lounge room, and the light from the sun 150 million kilometers away are connected by the same physics, the same Maxwell equations, the same electromagnetic field. Feynman called Maxwell's discovery of the electromagnetic equations the most significant event of the 19th century. Not a war, not a political revolution. 4 equations that unified electricity, magnetism, and light into a single beautiful framework. And it all started with the question of what really happens when you flick a light switch. So let us bring it all together, Feynman style. Everything your school textbook told you about electricity was a useful simplification, but not the full truth. Electrons do not carry energy through a wire like water through a pipe. They drift unimaginably slowly, about 1 millimeter per second, while the electromagnetic field propagates around the wire at near the speed of light. Energy in a circuit flows through the electromagnetic field in the space surrounding the conductors, described mathematically by the Poynting vector, not through the electrons inside the wire. Voltage is a property of the electric field in space. Resistance is the transfer of field energy to thermal energy through electron lattice collisions. And the light in your globe is the same electromagnetic phenomenon as the fields in your circuit, just at a vastly higher frequency. That is electricity. The real version, the Feynman version. If this video rewired how you think about electricity, smash that subscribe button and become part of the Curious Physics AU family. This is exactly the kind of physics I love sharing with you every week. Drop a comment below. What surprised you most? The drift speed of electrons? The Poynting vector? The connection to light? Tell me what blew your mind. Share this with your physics classmates, especially anyone studying HSC or VCE circuits right now. This context will make your understanding so much deeper than everyone else in the exam room. I will catch you in the next one.